Okay, let's take a look at our third Bessey shuffle for today. Now remember, a shuffle is a Bessey shuffle if it preserves Bessey sequences or inverts. So it needs to preserve or invert Bessey sequences. Well, the claim is all of the shuffles that we're going to feature in this little series are shuffles that preserve Bessey sequences. So therefore, by definition, they are Bessey shuffles. So this next one is going to be also a dealing out into 4 piles with judicious stacking. Now, one of the reasons I chose that word is you can't randomly stack these 4 piles. Just randomly stack them and expect that any particular structure will survive that, because it won't, okay? But this is far more complicated than just stacking from left to right or right to left. You're doing kind of this leapfrog stacking. But nonetheless, this stacking will preserve the fundamental structure of Bessey sequences, which is amazing. Okay, so the claim is the cycle notation for this permutation is the following. In fact, it's a product of 4 transpositions. That's interesting. We're just switching the objects in pairs. That's all we're doing. Well, let's see that happen here. So we begin with our ordered packet, as always, 1 through 8. We'll perform the shuffle. So this is pile 1, 2, 3, 4. 3, 4. Very good. Now what we're going to do is we're going to stack. This is 4. 4 goes on top of 2. 3 goes on top of 1. And then we will stack the right pile on top of the left. Okay, so once again, this is the leapfrog stacking that I've used in the Bessey sequence videos on this playlist. Okay, and now finally we're going to stack right on left. Okay. So what does that give us? What's the new ordering of the cards? Okay, well, this is what we get. So let's just check that that's what I got here on my piece of paper. So we started with 1 through 8. We performed the shuffle, and we got the new ordering 8, 4, 6, 2, 7, 3, 5, 1. And that's what we got. Okay, now changing that to cycle notation, we find quite readily that we get a bunch of transpositions. 1 goes to 8, so we have an arrow from 1 to 8. 8 goes to 1, so that wraps around, so that is completed. That's a little 2 cycle. 2 goes to 4, we have an arrow from 2 to 4. 4 goes to 2, so that wraps around. That's another transposition. 3, what does 3 do? 3 goes to 6. 6 goes to 3, so that wraps around. And finally 5. 5 goes to 7. 7 goes to 5, that wraps around, so we get a 4th transposition. Okay, so what happens with the color coding here? Did inversion occur, or did we just preserve these sets A and A complement? Well, inversion did occur, right? Because remember, 1, 4, 6, 7 are designated as members of the set A and are color-coded black. Position values 2, 3, 5, 8 are members of the complement of A and are color-coded red. Okay, so this truly is an inversion. Each value gets sent to a value of the opposite color. And so I don't know if we'll demonstrate it, but what that means, and this is something you can try on your own, it won't take much work, but if you start with a packet like this where you have 1, 0, 0, 1, 0, 1, 1, 0, and you perform this shuffle, you'll end up getting 0, 1, 1, 0, 1, 0, 0, 1. So inversion occurs. And I should point out the graph for the 7th shuffle. So it's over here, bottom left. As we've seen, we're looking at 4 transpositions. What you should expect to see are double arrowed lines between some red value and some black value. Okay, so 1 goes to 8, 8 goes to 1, 2 over here goes to 4 down there, and 4 goes to 2. 3 over here goes to 6, and 6 goes to 3, and then 5 goes to 7, and 7 goes to 5. And then we've indicated that inversion occurs.